And handing it over to Hanno.
Hello, good evening. This is year 7 in my world tour of robots, and it's good to see everybody here. Yay! Okay. So I'm going to start off with a 20-second or so video of the future. Here we go, the future. Okay, who's impressed? Yeah, all right. So it's Father's Day is coming up, so maybe I'll get one of those. I'm a proud dad, or maybe I'll have to get one for my dad. And what you've seen there was done last year by Felix Baumgartner, but of course there's enterprising individuals, and there's a company called Solar System Express, and they are developing a spacesuit including a gravity development board, which has a parallax propeller on it. And that's the main interface between all the different components, the rockets, the telemetry, everything else in that system. And there was an article in the Universe Today blog on May 22nd, so earlier this week. And there's a quote that this new gravity development board is easier to program via 12 blocks, the powerful, intuitive visual language used for robotic programming. Engineers, artists, and designers are thus enabled to create any project they can imagine. All right, so with that introduction, I will introduce 12 blocks and myself to you guys. So about me, that picture was taken a little while ago, before my kids, but I still use it. I got my computer science degree from Stanford. I started my high-tech career here in Silicon Valley, at Verity, at Yahoo, and at Oracle. And I moved to New Zealand 7 years ago to have fun with lots of robots and hobbies and my kids. And one of those projects was the dance bot, which I showed at an earlier tour here at HBRC. And that was actually featured in Circuit Cellar's 25th anniversary edition as one of their favorite projects in the last 25 years. There's a little tiny picture here of the dance bot. And that's the 25th anniversary edition from the Circuit Cellar. And I've also written some books. So I was a co-author of the Multi-Core Propeller Guide, and I'm the author of the upcoming Advanced Control Robotics book. And I've developed the Propscope, a USD oscilloscope sold by Parallax, the viewport software with which engineers are programming with the Parallax propeller, the T-Bot robot, and 12 blocks. My current passion is to teach with robots in schools, so I spend quite some time each week going into different schools, kindergarten, university, and taking kids either to competitions or teaching with robots, and I'll get into that. So what are some challenges facing schools? So lots of different abilities out there. Teachers are always stressed. There's less and less time and resources to accomplish things. There's standards out there that need to be met. And the future is highly uncertain. So there's globalization, China, India. The technologies are rapidly changing. Are we going to have artificial intelligence in 10, 15 years? And what will all of that mean for jobs? What we're really trying to do in education is prepare kids for the future. And so that gets me to what can I do to help prepare my kids and other kids for the future. And so the one thing that I think remains the same is that STEM, so science, technology, engineering, and math, will be incredibly important right now and also in the future. And sort of a left or a right way of approaching this. So on the left I have the old-fashioned blackboard, lots of equations, studying things by the book, memorizing complex formulas. And on the right, what I think is the right approach is to use robots. So to get kids to solve problems, give them more and more complex problems, and have the kids learn by doing. And what that helps is that you have all these abstract concepts in mathematics, physics, chemistry, biology. And with robots, I think you can turn some of those concepts into hands-on learning experiences. So there's 3 different approaches that I use to teach with robots. One of them is competitions. And there's all sorts of different competitions out there. Some of these fill huge stadiums, so 100,000 people going to an event to watch robots compete. So a scaled up version of the tabletop challenge. And this is great for all sorts of robot enthusiasts because it's a challenge. It's something that you can go to year after year, get better at, improve, learn from the experts. In Christchurch, my kids are 7 and 8 years old. My daughter is the one with the pigtails here and on the Maker's Fair poster. And she started when she was 5 years old. And when she was 5, she flew up from Christchurch up to Wellington, so a 45-minute trip, to compete in the National Robotic Challenge. And there's different challenges. One of them is to stay within a box, but to dance to music. And so the kids choreographed this routine using multiple robots with lights and servos and movements to do something creative. And obviously different kids were good at different tasks. My favorite story about this is that the girl who was picked to do the choreography and to dance really well, that's this girl over here. So that's the box that she was pigeonholed. She was a dancer girl, and that was what she was supposed to be. And she had a lot of fun with 12 blocks, and so she's really excited about programming now. So someone who was, through robotics, discovered something else that they were good at. Slightly more complex is a junior maze, and in this you aren't pre-programming everything, you're reacting to sensor input. And they use different tiles with different types of lines on them. They can include hills and other obstacles. And they need to navigate a maze, go to a special area, and at the later level, lift up a can and move it out. So quite complex, and you're using real-world conditions. So the lighting and different robots, different layouts. And I think a lot of people know about the first tech challenge, the first Lego League. So these are the 100,000 type events where there's a lot of teams spending a lot of money to compete at this level. And last year we were fortunate that one of the teams was powered by 12 blocks. So they used 12 blocks to program everything on the robot. That team actually included a kid who was dyslexic and couldn't program with textual languages, but with the help of 12 blocks, they were able to write a program that was able to compete at that level. Approach 2 is topic-based teaching. So there's some teachers that are highly gung-ho to escape the school and take a bus and go to competitions. There's others that say, I am a science teacher, I want to teach science, and I want to teach at this level. So this is topic-based teaching. And robots are very versatile. They can be used in all types of different lessons. I'll show you the topic map in the next slide. And activities can cover multiple topics. So look out there and see what's out there, and then pick a topic and see what you can do with a robot. There's robotic labs, and robots can be used as a textbook to supplement or to replace the material that's currently taught. So here's an example of a topic map with a robot and the different disciplines that are taught in schools, physics, math, biology. And let me go through some examples. Brownian motion could be taught in a high school biology class, where you, on a piece of paper, see that particles move around randomly. And this can be difficult to visualize, and with a robot. Here's a T-bot with a very simple 12 blocks program, randomly moving around in this box and causing that box, which is a larger particle, to move in a jerky Brownian type motion. Lunar Lander was quite popular 15, 20 years ago, and you can simulate this again with a robot. So here's a moon and a robot that has a proximity sensor that senses where the moon is and then uses calculus to make sure the position, velocity, acceleration are all appropriate to gently descend, so to drive up against the moon and not move the box. So that's a good challenge for kids. The third approach is a robot curriculum. So to really use robots as teaching tools across almost all subjects. And there's a couple schools around Christchurch that are doing this from kindergarten level up to 8th grade and in high school. And they're taking the official curriculum. So, for example, in New Zealand there's the NCQA curriculum that mandates that kids learn all these different types of formulas and concepts, and they're mapping those to activities that can be done with robots. And the concept is that the students climb a robot ladder by mastering the concepts and skills at each rung, and then they move up until they complete the curriculum. It can start very simple at the kindergarten or at the young level, where instead of real applications and complicated code, you're using these app-like blocks. So this is real code in 12 blocks, so there's a start block and there's a play tune block, and the play tune block has a piano that pops out and you click on the notes and that composes your tune. And then a dance one where you get a different types of movement and the kids click on them to create the code. And it gets more complex, so at senior year there's a video and PDF on the website that talks you through taking a T-bot robot and turning it into a error control robot, where you interact with the robot by flipping these tiles, and the robot will read the tiles as it moves over them, and it performs a parity calculation and tells you if the tile has been flipped or not. So it's a magic game applied to robotics. Okay, with that, I am going to go into lots of demos. I always promise lots of demos, and with everybody crossing their fingers, I hope to be successful. So here we go. First one is going to be 12 blocks. Here we go. And we're going to take a Arduino robot, which I think we have right here. This uses a Arduino Nano board, the Nano board. And it's still a prototype. We're getting pretty far along. It's made in China. And it has a whole bunch of sensors and encoders, a gripper, which goes up and down and closes, as well as a 100 by 100 LCD screen. But let's just start very simple with this. I'm going to plug this in. All right, that works. And I'll hold it over here, I guess. And make sure I'm on the right port. So that's 61. So this is 12 blocks. And 12 blocks has a worksheet. It's over here. And it has a library. And it has a library for different types of devices, ranging from parallax devices, like the parallax basic stamp, to the parallax propeller, like the demo board, or the parallax scribbler, but also includes things like the pickaxe and the Raspberry Pi, as well as different types of Arduinos. And for these types of devices, you just sort of click on them and you have different ways of configuring them. So I'm going to use the robot there. And we need to make sure we're using the right COM port to connect to that robot. And I'm just going to start this program. So to run it, I just click on the run button there. And let me just try again. So it's taking the program that I have here in 12 blocks, and it's now uploading it to the robot, and it's connecting. Okay. Oh, another microphone, that's good. Yep. Oh, that's okay, I'll hold it. Yep. So I'm a little happier now, so things are working, so now I can be a little bit more relaxed. So what this program actually does, and I'll build a program from scratch in a little bit, is a start block starts out a program. And then there's a move block to move 100 millimeters, so 10 centimeters forward. And then there's a repeat loop, and it's reading an ADC, and it's waiting between samples. While it's doing that, so it's a multi-threading program, it's starting and then playing a score. Okay, so it's relatively readable, and all of these are blocks that I can just sort of drag around. I can get them, I can put them back into the library or get them from the library. So here's a block that I can take it down here. And if I want to change the behavior of a program, I can click on any of these yellow boxes. So if I wanted to change the tune that it plays, I can click on this yellow box, and I can click additional notes. So here's a C note, here's an E, and here's a G. I can change the duration and sharp notes and all that sort of stuff. I can change the text version, so I can backspace here in the text. And then finally I can hit OK, and it'll update that in this box. If I wanted to go backwards instead of forwards, I would click on this arrow and go backwards, and that would be that. And this is just a text box where I click on it, and then it asks for the amount or an expression. So you can type in variables, you can type in formulas, you can type in whatever you want into these text boxes. And so let me just expand this a little bit. So this is a program that's visually developed on 12 blocks to run on a Arduino, and it's a multi-threading program that plays some sound, makes the motors move, and sets a variable to a sensor value. So in this case, I'm just reading an ADC on a certain pin. What I have down here is a real-time graph. So I'm going to graph the value of X. And X, I'll show you, will change based on which button I'm pressing on here. And you can also see the value over here. So let's run that again. So I'm just going to run that program. And I'll get the sound playing, I'll get the motors turning, and then I'll show you the value of X updating and being graphed in real time. So it's loading, it's connecting. So as I change the, let me try one more thing. All right. So the ADC is connected to, ADC3 is connected to these two buttons, and when I press them, they should give me different values. So there's 1,000, there's 600, and here is 800. So it's a very useful way of taking a program and seeing what's happening with the variables that are running in your program. So I'll just show you the real-time graphing. So I need to make sure that I have X selected for graphing. So I can go in here and check X, and let's try this one time. Okay, sorry about that. So here's the graph at long last, and what it's showing you is a time scale on seconds. We can change that to whatever we wanted. So we can go in the yellow parameter region and change the time scale to, let's change it to half a second per division. And we can graph multiple variables at once, or in this case just one because we only have one. And we can either use auto scaling or we can define the minimum and maximum. And here we're at 1,000 right now, so 1K. And when I press a button, I get the different values that I'm reading in over there. Okay. So let's go on to a slightly different demo. So I'm going to show you a little bit how to create a program. So I'll just put this off on the side. And we always start with a start block, and we get the start block here from the library. So I'll just start from scratch there. So here's a start block, and then I'm going to have a repeat loop. And any block that's inside of this repeat will get called over and over again. And all this code is running on the Arduino or whatever sort of robot you have. And I'm going to put an if in there, so conditional. So I'll just drag that in there. And I'm going to read my input. So here's a read ADC on pin 3. I just click on it like that. And to turn it into a condition, I'm going to just type it in there like that. So now we have start, repeat, if it's less than 900, then we're going to, just for fun, we're going to move forward and turn for a bit. And let's turn a little bit further. Okay. This time, we're going to set a breakpoint. So 12 blocks is quite easy to use, but it's also very powerful. So a lot of the tools that you get in things like Visual Studio, Eclipse, where you're doing very advanced programming, you can do that here in 12 blocks. So we can take one of these blocks and we can turn it, we can toggle the breakpoint. So now we have a little block, a little red square next to that one. And that indicates that when execution gets to that point, the program's going to pause. And we're just going to do one more thing so we can see what's happening. We're going to use the change x by 1 block, and so we'll put it here in the middle. So we'll stick it there, and we'll see the variable values down here when we run the program. So let's go, and we're going to debug this program this time. So start debugging. So it's uploading this, and if we don't press any button, we know that the ADC value will be higher than 900, so nothing will happen. So nothing is happening, which is very good. But now, the second that I press a button, so I'm going to press a button, the breakpoint was hit. Okay? So instead of keeping running, the program paused right where I wanted it, and I'm seeing that, yes, at this point, it's paused. From here, I can single step through these blocks. So I can go to debug and hit F6 or click on here. And so when I click this, the wheels should spin because I'm trying to move forward. So they moved a little bit and move forward. And now the execution is at this block where it says change x by 1. So x is currently 0. And so now when I'm going to go up here, debug, single step. The only thing that should change is that instantly x should go from 0 to 1. And so x is now 1, and I'm at this step. Because this is 12 blocks, I can change variables just by clicking on this and typing a new value. So I can change this x to 5, just for fun. And I can also change the parameters that are used in these blocks. So I can say the next time that you go here, I'm going to increment x by 2. And now I'll keep running the program. So I'll go to debug and resume the program. So it did the turning, and now it's just sitting there. When I press the button again, it's going to hit the breakpoint again. So I'm hitting the button, and it hit the breakpoint. X is still 5, and now when I do another single step, debug, single step, it moved, and now X is 5 in the Arduino, and now when I hit single step again, it incremented by 2, so we've shown that you can change both the constants and the variables in the running program while the program is running. So these are all things that you can't do with an Arduino currently. You can't do multi-threading, you can't do debugging, you can't set breakpoints, you can't do single stepping, you can't do real-time graphing, you can't change parameters, you can't change variables. And you also can't program it visually like this. So lots of things. Question? Yeah, okay.
Is the program
Let me turn that on.
Yeah.
Is the program 12 blocks free?
There is a free version that lets you write very simple programs. So as long as you're writing a very simple program, you can get the feel of what 12 o'clock is like. If you're using more complex things, longer programs, then it's $79.
Oh.
Okay. All right, so these are some programs, and now we're going to go to one more. And again, it's a pretty simple program. It sets X, Y, G, and A. Those are some variables. It sets them to some amounts. And then it sits in this loop. So it sets SW to that ADC value. And we're going to just replace that with this one. And then it sets the motor speed and the servos 9 and 6. So looks pretty simple. There's certainly no Bluetooth code in here. There's no parsing, nothing that would indicate that this integrates very easily with an Android tablet. So what we're going to do now is we're going to run this code. So it's taking this code, converting it into C code, and I'll show that to you in a little bit. So you can always click on View Code and see what type of code it's creating. And it's uploading it, so there we go. See how Bluetooth is in this building. So I'm going to put this here, turn it on. Here's my regular Android tablet. Toughest part is finding the on switch. Okay. And I'm going to connect to Bluetooth. Give me 1 second. So we're going to connect, and here's the robot. And it says I'm connected. So let's see if we are. Oh, forgot one thing. This is the Bluetooth module. Without this, it doesn't work. Okay. So we take this Bluetooth module and we plug it in. Sometimes I have little to-do lists which I use in demos, sometimes I don't. Okay, so we'll try that again. So there it is. I don't know if I'm still connected. Let's see. All right, and we are connected even with all that. All right, so I have here a little Android app, and this is a very general purpose Android app. Notice that there's nothing special about this program. The only thing in here is that the order that I declared those variables matters. So there's an XY variable, and those are used to manipulate the motor speeds. So y plus x for the left side and y minus x on the other side. Pretty simple math. And what that means is that I can hold down the tablet, and then when I tilt it forward, it moves forward and backwards, and then I can turn it and sort of drive it around. So remote control toys are much simpler and easier. So what I'm trying to get across is that this is very general purpose. This isn't an app just for driving. This is an app for taking an Android and connecting it with an Arduino. And I get information from the sensors fed to the tablet, and I can use the accelerometer and the gyroscope in the tablet to control the robot and make it move back and forth. And there is a joystick on here as well. And with the joystick, I'm controlling G and A, so the third and fourth variable. And the third and fourth variable are used to manipulate the servos. So the only code running on here is what you see there, nothing behind the scenes. And with this, I can lift and lower the gripper, and now open and close it, and sort of do all this at the same time and all that. See? Yay, can't flex it. You can see it sort of spins quite rapidly and all that. So. Okay. That's like 3 or 4 demos, but I have more. Okay. So these come in a Arduino and in a Parallax Propeller version, and look for them on the website in about a month. Next one is the Lego Mindstorm. So here's the Lego Mindstorm. A lot of schools go for this by default in the beginning because they're Lego and people know Lego. And 12 blocks supports Lego. So we're going to just plug this in. We can also use Bluetooth, but we'll just plug it in for now. So we've turned this on, we get the Lego sound. I'm done with this window of 12 blocks. Now I'm going to change it, go away. All right, here's another one. So here's the NXT program. Something that I want to show you here too is you can start off in interactive mode. So we can click on the control button, in which case it connects with USB or Bluetooth to the device, and now you get control over the robot. So from here I can click these buttons and make the robot beep. I get the sensor values down here. So there's the touch sensors and the ultrasound. You can configure hardware and tell it what sensors you're using and all that sort of stuff. But this is a first step that people can do. They can just take the robot and control it remotely from their laptop, and then build up a script of code that can be inserted into the program. So that's interactive mode. Here is a very simple program that you can just click on the run button, and it's now loaded in here. And I disconnected that, and now when I'm here and press a button, it moves forward. And the way that looks like in 12 blocks looks identical to the other program, the Arduino ones. Start, repeat, if touch on sensor 1, then move 100 millimeters forward. So the beauty of 12 blocks is that it's one visual language that supports all these different types of devices. So professors wanting to develop a curriculum for one robot get all the other robots for free. Currently, there's already quite some documentation and tutorials and videos doing the things that I talked about. So curriculum developed for 12 blocks. But there's a bunch of other activities going on right now. So at the University of Winnipeg, there's 14 students, so these are teachers, that are enrolled in a class called Teaching with Technology. And they're using Lego Mindstorm with the simulator that I'll show you in a bit and 12 blocks to develop activities and curriculum for teaching with technology. And so in a couple of weeks, we're going to have tens of additional activities for 12 blocks. And there's multiple of these efforts going on right now. So it's mushrooming. Yeah? Why is it called 12 blocks? So my philosophy is that when you're starting out programming, you're not going to write a 1,000-line program. You're going to start with something relatively simple. And so all the programs that I show right here and that I include in my tutorials or that I expect people to show others are going to be programs that you can copy by doing very quickly. There's one school of thought that you learn by programming by downloading a 1,000-line program from someone, hitting the run button, and you're done. My school of thought is you should take one block at a time and see what that block does. So a start block starts a program, and then you move, and then you do a repeat loop, and you build up from there. And so I call it 12 blocks because I think you can do almost anything in 12 blocks. So if you want to do a multi-threading Android-powered program that makes servos move up and down, sends sensor values back and forth, turn around, do addition, subtraction, that program that I showed you here with the Arduino was a 12-block program. This is a very simple program, so this is only a 4-block or so program. But inside of 12 blocks, you can do a whole lot. 12 blocks has hundreds of blocks. So there's a couple hundred blocks here, and it depends. You can say, I want less. So if you're not an expert, you can say, I want only 34 blocks, or I want the full blocks. And if you pay for the license, then of course you can use any number of blocks and all that. Yeah?
I have a quick question, because there's lots of different robots here. What does it mean, move 100 millimeters? Isn't that robot specific? Where does that magic compare?
Okay, so the question was, where is the magic that maps the different robots to their distances and so on? So you can go into Mindstorm, and so this is the device manager, and you select different devices here. And over here on the right side is a device-specific configuration. So the Mindstorm has 4 inputs for sensors, and currently I have touch, red light, and ultrasound, because those are the sensors that I have connected to it. And the configuration here is that the move C constant is 21 and the turn C is 19. So these are these magic numbers that do exactly what you were referring to. They map 12 blocks millimeters to the device. And you can see there a little note that if you have a wheeled one or a tracked one, you should change those. And different devices, so here's the Arduino. You can put things on different pins. So if you wanted to change that, you would change that configuration there. So here it says audio pin equals 11. And this one also has a move C and a turn C. Okay? So there's these constants that you can change, and there are defaults for all the different ones out there. 12 blocks is configured by lots of XML files. So all of this is in an XML file that more serious expert programmers can change and can then customize 12 blocks for their unique robot or for their teaching environment. And it's that flexible that if you wanted to add support for a whole new architecture, then someone else, without my help, can do that. I'm not going to guarantee that that's possible for everything, but someone went out there and said pickaxe is not supported, and then went very far to supporting it. I ended up doing some work in addition to that, but it's a executable that I own, but there's lots of ways to customize it. Okay. I was showing the Lego Mindstorm and it moved and you could control it. So that brings me up to my next demo. We've done Android, we've done Arduino, we've done NXT, we're going to do simulator now. So Cogmation is a company that has been doing robot simulation for a decade or so. They started off doing multi-million-dollar robot simulations, so big machines and factory floors, making sure that they're not running into things and that they're safe. And they're now getting into education. And so I partnered with them last year. And they have a program that I think I have to start up. So it's called Robot Sim Edu here. So this is from Cogmation. It's called Robot Sim. And they're a Canadian company. That sells this software in Canada through a distributor called Spectrum. And so with our partnership, we're selling 12 blocks, Cogmation, and a curriculum developed for Lego Mindstorm robots. We've done a good number of deals at the classroom level, at the school level, and we're now at the Providence level. So a whole bunch of schools looking forward to using 12 blocks and Mindstorm. So they have lots of different tutorials, lots of different environments where you can do robotic type stuff. We're going to go to the Sumo Environment. Okay, so we're loading the Sumo robot environment, and what you'll notice is that there are two robots. So there are two Lego Mindstorms, and I'm not going to open that. They're sitting here in this ring, and luckily I have two 12-block windows. So here's one window for the left robot, my nice comment tells me, and here on the other side I have one for the right robot. And see if I can move that window there so we can all see it. So this is the same 12 blocks, looks the same. If I plugged in a cable, then my robot here would move forwards and backwards. But because I told it over here that the mode should be Robot Sim, it's going to do everything in the simulator. And so I've attached this 12 blocks to the left robot and this 12 blocks to the right robot. And so now all I need to do is start the simulation. So this is, has a physics engine in it. It does the ultrasound and the speed of sound and all that physics stuff. And it's a 3D environment, so I can look and do all that in there. And these robots are now being simulated. And now I can click the run button. It'll connect to the communicator and make that robot move. It's very simple, so just moving back and forth. Here's another one, and this one is connecting to the other one, and so they're moving around in the simulated environment. They have different environments, so one of theirs is that they simulate playing golf on Mars. So they have the same Lego Mindstorm. They have a builder tool as well, where you can choose different bricks and move them around, and you can program all of that in 12 blocks. All right, so let's stop that, and I think we're on the last demo. So we're gonna exit there. So this is a robot arm. It's a Lynx Motion AL5B, I think. And we'll just move it out here. And it's connected nicely. All good. So, what question?
How do you put what kind of, I know it's a Lego NXT, but how do you put what configuration you have? You could build anything with the Lego NXT.
So I showed you that in 12 blocks you can change the device configuration, what sensors are plugged in, and for the simulator, that there's a tool that lets you use Lego bricks and build stuff.
So, okay, so the simulator knows where the sensor is and everything.
Yeah, so that's a question for Cognation. So I'm not an expert on that, but they have a tool called Sim Build or something, where you start off with a bag of any bricks. It's a simulation, so you can have as many bricks as you want. And they have the physics of how big one is and what the weight is and center of gravity and the electrical connections and all that. So you build in the simulator. They have a whole bunch of different environments, but if you wanted to, you can build whatever you want. They also have a simulator for the T-Bot, and my robots are in the simulator already, fully configured. So here we are with 12 blocks again, and this time we're going to use the move arm block. So this is a relatively new block. Chuck was a big help. Thank you, Chuck. And again, you click on a yellow parameter to change it. So changing how many times something repeats is as simple as changing the number. But if you wanted to change something like how you want the arm to move, for that there is something a little bit more complex. Okay? So this is the arm controller wizard. This is just a wizard for one of the roughly 200 blocks. And I'm just going to see if everything's working. Okay. So I'm just going to see which port I had here. Oh, it helps if I plug the cable in. There. USB cable. And plugged in. So let's see if I have my COM port now. There is 62. So now I click on there and I click on it's connecting and all that. So now don't be startled if it moves very quickly. Oh. It's not moving. Okay. It'll move very soon. Okay. No, not yet. All right. So things are working, that's good. And this was working at Maker's Fair continuously for Saturday and Sunday after I assembled it on Friday morning in an hour and a half or so. So give me a little credit there. So robot arm, 12 blocks. And we're going to start off by doing simple things. So here is a 3D rendering of an arm, and it has lighting and all that sort of stuff. And here's the grippers opening and closing. Let's see, where are we? There's a gripper, and it opens and closes. Not too hard. Here is a simplified view of the side view of the robot. So you can see that it's going up and then it's going sideways a little bit. And I can change these just by moving them. So each one of these joints I can change by dragging that appropriate point. If I wanted to do something more complex, there's a lot of math involved. So inverse kinematics lets you specify the position of a point, and then all the joints in the arm will figure out how they're supposed to move in order to get to that point. So if you tell the arm, I want to go here, then obviously this has to move a little bit and this can move, and so it's easier to show. So I'm just going to go to this point and now take the whole arm and move it sort of all around, and you can see all the different joints moving to get there. And we can say, we can move this, the last one, so move the hand, or we can leave the hand and take an internal joint and move that around. And you can see that the hand is approximately in the same space and it's trying to get there. So that's just moving the robot by hand, so that's me doing it. Does someone have a pencil or something? Maybe this thing, okay. We'll see. So the big challenge is to see if I can pick this up. Oh, yeah, that's probably, we'll see how it works. So pencil, random pencil, I've never met this guy before except for lunch today. I've put the pencil down, and my challenge is to program to pick up that pencil and then to do it a second time. So let me just see where we go. Let's see. I'll just show you one more trick. So these are keyframes. So these are positions that I've programmed before. This is what I was running at Maker's Fair. And I can go to a certain position by clicking on it. So I can go to that position, or to this position, or back and forth by clicking on these. I can also just drag the time cursor back and forth. And once I'm at a position, I can change what pose I want the robot to take. So these are the new positions I want to take. And you can see those lines on the bottom, which represent the servo's position. They're changing as I'm doing this. So as I'm moving this arm back and forth, I'm doing inverse kinematics to figure out what the angles are. And then I'm interpolating splines to give you the angles over time right there. So let's see which position of the robot arm was somewhat close, so I don't have to do all of them again. Let's see. So I think I'm going to change these. I'm going to delete this one and move this one there. Okay, so that's pretty close. If I go on this side, we see that that's still on the bottom. So I'm going to delete this guy too, because this guy over here is up there. So all we need to do is make this guy get closer to the pencil. So I'm going to edit this one, so I selected it. And first off, I'm going to make it go up a little bit. Now I want the gripper to go down. I need the base to rotate a little bit. There. Probably opening the gripper is a good idea. There, it's full open. And now if I go down, maybe out a little bit, that's probably pretty good. So I'm going to copy that on both sides. See how we do there. And so I go down to it. Whoop. I meant to do that. Okay. So the first one just gets the arm. So I'm faster that time. Was it rotating or why was it moving? Okay. So, okay. So we get there, and what I'm going to do to fix that is I'm going to open the gripper before it gets down there. So in this phase, I'll still have the arm a little bit up. So there it's up. So now we go down. And then on this one, I'm going to just close the gripper. So when it gets there, it will close the gripper. That's probably pretty good. And after that, from here on out, I have to make sure that this guy still has it closed. We'll see if we get there. Okay, so it'll be there. No, this is just programming it. So once we get there, at this point I want to rotate a little bit. So we'll create another one here that will be at the other side. That's pretty good. And then at this point we say that's a good place to drop it. And so we'll drop it right there. Okay? So that's me programming the gripper. So now I'll put it, I have to put it in the same spot. I'm still here in California for another 2 weeks. And my dad's really interested in combining computer vision and artificial intelligence and other things to do things that like a human could do. And a human could pick up that pencil, so we want to pick up the pencil with the arm and a webcam. There's already a fiducial block inside of 12 blocks that lets you look at a fiducial and get the XY coordinates for use in Arduino or Lego or whatever. But we're trying to see how we can pick up something like a pencil. So let's see, we're going to play this. It's going to play to the end, so it's going to go to the end. And now when I hit play again, I'm hoping that it picks up the pencil. we'll see. So it goes there, goes through all these motions there, not getting harder, and it drops. Okay, that is it. That's the last of my demos. I'm glad it worked. And the next slide is just if you have any questions.
So do you have block tracking there in your program?
So the question was, is there blob tracking in there right now? With Viewport, there's an OpenCV integration, so you can do whatever you want, and there is blob and color and other stuff, circle. But with 12 blocks, I don't have blob detection in there yet.
Okay, hold on. People can't hear the question unless we use the mic. So people who want to ask questions, just raise your hand and we'll get you on mic. So you're going to get the first mic. Who's next? Okay.
Are those robots with kits, or the ones with Arduino and the Raspberry Pis, are they with kits?
I'm a computer software guy, so my idea is that if you want to learn how to do Lego blocks, you buy a Lego kit. If you buy a robot, you get the robot as is, and you put in batteries and you're off and going.
But you could make any configuration robot out there and program it in
the robots that I sell on my website are ready to go. There's no kit. There is a hacker port, so there's voltages of 9 volts and the battery voltage and 3.3 volts and a bunch of different I/O pins so you can interface with the Raspberry Pi or what have you. And then mechanically you can add onto it as well, so there's mounting holes and all that. But my philosophy is that you buy a robot and here it is. There's a sample program running in it and you can make it do stuff right away.
Who's next after this?
You mentioned that underneath the cupboards it's generating C code, and I was wondering if you can, I'd like to see that, and I'm also wondering if you can edit the C code that you see, like if you make changes.
So here's a Mindstorm, and the Mindstorm, the language that I use is NXT, not exactly C. And so you can always do view code, and here is the code in a editor, and here is the code that we're sort of writing there. Okay. So here in the actual program, there's a start, repeat, move 55, turn 90. And here's the while true, move, millimeter, move, degrees, and then motor set, and that's a task, so you can do multitasking. And here's the proceeds that sets up that task, and then there's other things in there. Propeller is currently the only language that I support there and back. So let's just take this complex program here and turn it into a Propeller program. Okay, we're done. And now when we click on View Code, we get a code editor, but this is, it has those numbers in there. This is not guaranteed to work, but we'll see. I'll give it a try anyway. I'm going to change one of those numbers, and I'm going to change that repeat statement from a repeat forever to a repeat 10 times. So I've made 2 changes. You guys want more, so I'm going to add a whole new statement. Okay? And I'm saving this file. Now, when I go back to 12 blocks, it says, do you want to reload it? Because it says something has changed in the universe. And I say yes. Sorry. And here is the program. It says repeat 10 times, move 155, 155, 55, which is matching what I changed here. This is totally not guaranteed to work with all phases of a moon and all that, but it's there to show the student that behind the scenes there's no magic. So they can always do view code, see what's behind there. They can even copy blocks and paste them as text and back and forth. There's a whole web community type stuff where you can upload programs and download them. But yeah.
That's really nice. If you do something that it can't bring back, can you still tell it to run from the text?
So we'll do that. I think I have to close this. I'll just be sure. So here's this, and we're going to do crazy stuff here. Just for fun, we'll copy that and put it in here. So I think that part should still work, but if I write HBRC is cool in there, all right, and now save this. We'll see if the lights flicker. If you want to reload it. Okay, so it's done a pretty good job. So that's what we end up. Okay, so it did figure out that I have this nested loop, and I have all these, and then HBRC, it detects as a function call in that case. I didn't show you guys functions, but it's really cool. You can refactor, you can do lots of cool stuff. You can import worksheets and all that too. If I try to run this program, I can click run. Oh, this is, I'm still in robot sim mode. If I run it on a device, it's going to say expected end of line dot HBRC is cool. So it's going to tell me that there is, and it highlighted my block. So I need to fix this block. And of course I can do that just by taking this block and throwing it away. So this is a valid program again. It's going to no device found for, yeah, okay.
Hanno?
Yep. Hi,
Is
Cam.
Is the HBRC in Christchurch still active?
We had a visitor recently, that was Steve. I don't see him now. There he is, yep. So Steve can tell you more about that. He visited us maybe 2 months ago, and Steve, is it active?
Yeah, in February. Yeah, that was really cool. I had a really neat time. I got to see Christchurch, which is in an interesting point right now. Lots of stuff that's open, lots of stuff that's not. But it was really cool to go to the KiwiBots meeting, which was at a radio device company, and there's a lot of people working on some really cool stuff. Very, very interesting. Lots of hacking going on. I was really I think I gave like a brief trip report. March meeting, or maybe the February meeting. I think we got back just in time for the February meeting. But yeah, I really like the EDM machine that the guy, the guttering electric cutter that the guy built with using in his XY platform was filing cabinet rails. I thought that was really cool. And then there was a guy who built like a whole audio equalizer graphic display system totally in FPGA. No libraries, no Linux, no assembly, no code, just all FPGA gates. So there's a lot of those.
So we're a friendly bunch. Come visit. We took good care of Steve. He's back here.
Yeah, your sister club. I had to pay a visit. We organized the trip. We re-engineered our itinerary just so I could make the KiwiBots meeting, and it turned out to be pretty cool. It's a smaller group, much more intimate, but everybody ought to check it out if you get down there.
Yeah.
More questions? No more questions. Okay. Well, I'd like to please give a big round of applause. I'd like to point out that what Hanno did with the arm there, if you wanted to buy industrial grade, you'd be spending many thousands of dollars to be able to do that. So just to sort of give you folks an idea of what's going on there.